The surface energy, particularly for nanoparticles, is one of the most important quantity in understanding the thermodynamics of particles. It is surprising and to note that still great uncertainty we have about this value. The uncertainty is about dependence on particle size. With respect to the thermodynamics of small particles, the surface energy is an essential and many cases dominant quantity. We have discussed the brief discussion of surface of nanoparticles in the last lecture. In the last lecture, we have also discussed the surface to volume ratio and the dramatic change in that ratio. Now, after understanding the surface to volume ratio and existence of surface energy, we will discuss it in detail in this lecture. This is the syllabus of this unit, and we are on the surface energy, physical chemistry of solid surfaces. The surface always have possess some energy, and this energy is crucial for understanding the behavior of particles and decoding the size of the particles. In this lecture, we will study the significance of surface energy, then the mathematical formulation of surface energy, possible models to calculate surface energy, and some examples from some various crystals. In this lecture, first we will review the origin of nanostructure and nanomaterials about surface energy. Then we will discuss possible mechanism for a system or a material to reduce this surface energy. In fact, what is the cause why we are having that stress? It is true then that the surface energy or is always there with all kinds of solids. But here, in the case of nanostructures, it plays a very crucial role. In the case of nanomaterials, as we have discussed in the last class, that when we reduce the particle size, then this reduction results in more surface. And not only more surface with respect to volume, but the ratio is very high. And that is why we obtain some good results. some exciting results with nanoparticles. The surface energy always play a role with the solids, but in this case, very high increment gives some different results. And that is why sometimes the structures take some particular values, some different shapes. It helps us to study the thermodynamics of the crystals, thermodynamics of the nanoparticles. And ultimately, if you study the thermodynamics, then you will learn a lot of about the behavior of nanoparticles, how they work here. We know many things about surface of solids. On solid surface, or there are certain atoms or molecules, which depends on what solid is there or liquid is there. But these atoms or molecules who are residing on the surface, not inside the surface, they always have less nearest neighbors as compared to those atoms or molecules which are inside the solid. I think this is convincing to all. We know that the atoms are very close to each other in solids, and so many neighbors are there with the solid atom. But those atoms which are on the surface have less number of nearest neighbors. The reason is only atoms exist just below that surface. There doesn't exist any atom above the surface. So if any atom which is on the top surface can have only some neighbors and which already exist in downward side. Now the issue is those atoms which are on the surface have less neighbors, and we also know this word also gives you idea of coordination number. Neighbors almost synonymous to coordination number. If you are having less neighbors, then less coordination number will be there. That is the reason if less number are there, so they possess many unsatisfied bonds on the top side of the surface. These dangling bonds are very much responsible for many activities in nanoparticles. But before going into detail, first we understand these two, coordination number and dangling bond, in detail. This slide I have intentionally added to give you the idea of nearest neighbors. Suppose you consider red as the reference atom, then try to check the nearest neighbors, then next nearest neighbors. The nearest neighbor means neighbor which are at the shortest distance from the solid atom. Those are called nearest neighbors. And the next nearest means those atoms which are having length slightly higher than the nearest atom, distance slightly higher than the nearest atoms. So here you can see, if you take this as an example, then this red atom will have 12 nearest neighbors, and these nearest numbers are shown here in blue, green and yellow atoms close to this. Now you can also calculate next nearest, and that will be 6. Up, down, left, right and forward and backward. So this indicates you, whenever we discuss about the bonds, you must take care the nearest neighbor first, then come into next neighbors. Now this can be understood more critically in the next slide. Suppose remove all other atoms here, then corresponding to red, now you have 1, 2, 3, 4 and 5, 6 nearest neighbors here. So these are called nearest neighbors. And these nearest neighbors are very important. If the material, if the atom are inside the solid, it will have all nearest neighbors. But the question is, when some atoms are on the surface, then it is difficult to calculate nearest neighbors, because the number of nearest neighbor will decrease and the neighbor will be only inside the solid, nothing will be outside the solid, and that is why number will be less, that we have discussed in the previous slide. After understanding the concept of coordination number or the nearest neighbors, now the second thing that must be understood, that dangling or unsatisfied bonds. The upper surface which is free, if it is free from the top side, from the upper side, then it may have some unsatisfied bonds. Yes, the lower bonds are always satisfied, because lower bonds are always associated with other atoms, but the upper surface may have some unsatisfied or unoccupied ends. These bonds which are not satisfied are called dangling bonds. Basically, a dangling bond is an unsatisfied valence on an immobilized atom. Yes, these atoms are immobilized. It is solid also. An atom with a dangling bond is also referred to as immobilized free radical or immobilized radical, a reference to the structural and chemical similarity to free radical. Here in the picture you can see that those atoms which are inside the surface, I can mark it here like this. Suppose this atom which is inside the surface, this atom is bulk atom, and so it has all the atom. One atom is here, one atom on right side, one atom on top side, and so on. So it has all the atoms. But on other side, see here, the top surface, these type of unsatisfied bonds. These are called dangling bonds because these bonds are not satisfied with others as they are on the top surface. I'm showing here by arrow here. These are called dangling bonds. And since the atom is immobilized, these are called radicals. Immobilized radicals. In order to gain through electrons to fill their valence band, many atoms will form covalent bond with other atoms. That we know, we learned in the chemistry. Then the covalent bonds always formed between two atoms in order to fill their valence band, in order to complete the octet. If two atoms contribute one unpaired electron, then it is called single bond. This may happen in the carbon and hydrogen. Suppose carbon and hydrogen, both hydrogen have one excess electron and carbon has one less, then they can share one electron. It's called covalent bond. Two atoms each contribute one unpaired electron. Atom which possess too few bonding partner to satisfy their balance and which possess unpaired electrons are called free radicals. So now we have defined free radicals which have too few bonding partner. If the bonding partner is very low, less in number, then this possesses unpaired electrons. And this is also the story of atoms which are on the top surface. They are called free radicals. Now, in the case of solid, the radicals are there, but in the case of solid, these radicals exist in immobilized environment. Since they exist in immobilized environment, then these are also called immobilized free radical. So often, the molecules containing such atoms, when a free electron exists, on the solid surface, then these radicals are called immobilized free radicals. And actually these radicals are responsible for dangling bonds. Now the free and immobilized radicals display very different chemical characteristics for atoms and molecules containing only complete bonds. Since the complete bond atom, the atom which is not having any field dangling, are very less reactant to reactions. They are very less reactive. But on the other hand, these free radicals, immobilized free radicals, gives different chemical characteristics. Generally, they are extremely reactive, and immobilized free radicals, like their mobile counterparts, are highly unstable. Since they are reactive and unstable, they gain some kinetic stability because of limited mobility of steric hindrance. That, that is why you can say they may have some immobile regions. While free radicals are usually short-lived, immobilized free radicals often exhibit a longer lifetime because of their reduction in reactivity. And that is very important for us. Bonds are there, dangling bonds are there, and materials are there. We can check and study the behavior of dangling bonds. You can also understand more details by this figure. I must acknowledge Aalto University School of Chemistry for this picture. Very nicely explained the dangling bonds. On the bottom side, they have shown one solid here. And on this surface here, they have magnified this like this. Now in this, many atoms they have shown. They have zoomed out atoms here. Now in this, you can see they have pointed out two colors. One atom is outside and another atom which is inside this. Now any atom which is inside the bulk will always experience force in like this. All the direction you have force. This atom exerts force on another atom, atom exerts force on this. So all the atoms which are inside the solid may not have any unsatisfied bond due to this reason. Now the thing is, the atom which are outside the or on the surface, they are unsatisfied. Why? Because like this, you can see they always have force which are inside, towards inside of the surface. There is no force here like this. You can't observe any force here on the top surface. So that is important here. And due to this, they are unsatisfied. Now, because of dangling bonds on the surface, as we have seen, what are the dangling bonds? Because of these bonds, surface atom or molecule are under an inwardly directed force. They exert a force inwardly directed because there is no attraction on the top side. Surface is free. And the bond distance between the surface atom or the molecule and the subsurface atom is smaller than that between interior atom or molecules. This is obvious. The atoms which are inside the surface will have lengthy bond. The bond may be have higher length. But the atoms which are on the surface exert some special forces, and due to this tense behavior, the bond length is small. This concept of dangling bonds is dominant or significant for small particles. If the particles are large, it also exists. This may also have, you may also have the example of liquids. Liquids always face a stretched behavior on the surface. But solids also have some important characteristics, especially the particle with small size, nano size. When the particles are very small, this decrease in bond length, as we discussed in the last class, then the bond length may decrease for the top surface atoms. This decrease in bond length between the surface atom and the interior becomes significant. And the lattice constant of entire solid show an appreciable reduction in extra energy. This appreciable reduction in extra energy possessed by surface atom is always described in terms of surface energy or surface tension or surface free energy. The surface is always in a phase of tensed membrane, and something which is reduced as no atom is present on the top side, outer side. This reduction in bond actually reduce the energy, and that is why surface free energy come into picture. If we have surface energy, then we can obtain the surface energy. The surface energy gamma is the energy required to create unit area of this new surface. I think you may remember the energy definition from the surface tension practicals. In the case of surface tension, the amount which is required to bring one atom from the inside the atom to outside or on the surface is called surface energy. Same definition is here. You can resemble this. You can the surface energy in the case of small particles, nanoparticles, the energy required to create unit area of new surface, that is called surface energy. Here the formula is gamma is equal to del G over del A NITP. Ni is the number of atoms, T is the temperature, P is the pressure. This gamma gives you the idea of surface energy. Here obviously A is the surface area. The energy for unit area we will calculate here. See the picture. On the left hand side we have one rectangular solid, and then we have divided this rectangular solid into two pieces. Whenever we divide this solid into two pieces, you can see here other faces are already open. Whenever I am saying other faces means faces on the left hand side, faces on the right hand side, A faces on the top. These are already there. Similarly here. But we have created this new surface, new face here. Now these two new faces will create a system. Why? Because these new surfaces may have some atom, a large number of atoms on the top surface responsible for tangling bonds or surface energy. On this newly created surface, now each atom is located in an asymmetric environment, which was not before dividing this big cube into two small. Now after cutting this, atoms which are on the top surface are located in asymmetric environment, and this surface plays stress medium. Now the atoms from this surface have a tendency to move towards the interior because of breaking of bond at the surface. Initially there were bonds, but you break the bonds. Since you break the bonds, they have a force towards interior. Now the extra force is required to pull the surface atom back to this original position. If you want to get this one. Now we assume these surface as ideal and singular surface, and for each atom on this singular surface, the energy is required to get it back to original position will be equal to number of broken bonds. The number of broken bonds is given by Nb, and we can get the energy by Nb multiplied by half of the bond length, that is E. Therefore, the surface energy is given by this formula, gamma is equal to half Nb epsilon EPA, where Pa is the surface atomic density, the number of atoms per unit area on this new surface. So from here you can calculate the energy which exists due to breaking of bonds, due to bringing of some atoms on the surface. In the past slide we have discussed a crude model, but this model ignored the interaction owing to higher order numbers, and this assumes that the value of E is same for surface and bulk, doesn't include entropic or pressure volume contributions. But as a matter of fact, they also exist. There is existence of entropy, existence of pressure volume contribution. Since our assumptions are wrong, or you can say assumptions are approximated, simplified, oversimplified, they can give only a rough estimation of the true surface of solid surface. And this is applicable only to solids with rigid structures where there is no surface relaxation occurs. So I have used many terms. Suppose surface relaxation occurs. You can relax the surface, you can change the surface, then you have to take those parameters into consideration. Entropy, pressure, volume, and so many things. When there is an appreciable surface relaxation, such as surface of atoms moving inwardly, or there is a surface restructuring, the surface energy will be lower than that estimated by above equation. So basically it depends on where we want to use our agents. Approximation can be done or not. In spite of overly simplified assumptions, as we have used in previous equation, it does provide only some general guidance that we must keep in mind. We have to modify it whenever needed. Let us take an elementary crystal with a face-centered cubic structure. Here it is. Take this face-centered cubic structure. having a lattice constant of A as an example to illustrate the surface energy of various facets. Each atom in FCC has a coordination number 12. What is the meaning of this? The nearest numbers for this any atom in the FCC is 12. Now each atom on 100 plane facet would have 4 broken chemical bonds. I am talking about this surface. This surface is 100 surface, and this always face 4 broken chemical bonds if it is on the top. And in this case, the surface energy of this 100 surface can be calculated by this equation. Gamma 100 is equal to 1 upon 2 upon A square 4E, or 4E upon A square. This time we have calculated this energy for first figure. Similarly, each atom on 110 plane, as it is shown here, this is 110 plane, have 5 broken chemical bonds, and 111 shown in the third has 3. So basically this has 3, this has 5, and this one is 4. The formula for these two 110 and 111 plane can be done by this value: 5 upon root 2 E upon A square, or 2 root 3 upon A square. Now we can easily figure out that the low index facet have low surface energy. Thermodynamics tells us that any material or system is stable only when it is in state with its lowest Gibbs energy, and therefore a strong tendency for a solid or liquid to determine the total surface energy. There exists a strong tendency. So this is a key factor to study the behavior of nanoparticles. Now, how this energy can be reduced, we will discuss in next lecture the tendency of reduction of this energy.